Doc here with part 2 of our review for the first lab exam. Looking at your sheet, your review sheet, Lab 2, which you can open up as a PDF file online. Lab 2, the oscilloscope. So the first question here is, what is represented on the vertical and horizontal axis of the oscilloscope? Very important in all graphs in any course you're taking. Always understand what's on the horizontal and what's on the vertical. Here, this is time, and this is amplitude. And then you should know, like, what particular units are we using for time? Here we're using, this is going to tell us down here, that the time per division, the little division here, each of those divisions worth 1,000 milliseconds, which is 1 second. So that means this is 1 second, 2 seconds, 3, 4, and 5. And for the vertical, it says the volts are in 1 volt per division, volts per division is 1 volt, so that means the one block going up is 1 volt, 2 volt, 3 volt, 4 volt. Know that if I change these, then these change, and then I get different sizes, but the measured value will be the same, as we'll see in a second when we get to that one to review. So that's the first part of the review. What is meant by division? Division is a little baby block here. This block here is a division, and if you want time per division, it's telling you the amount that the block is worth from left to right, and the volts per division tells you what the block is worth up and down. So here the block is worth left and right is worth 1 second. So this is 1, 2, 3, 4, 5 seconds. The period is 5 seconds. The X and Y position simply shift up and down for Y. Y is up and down. Y is up and down. In other words, for your math class, you may have remembered in high school, they'll call this the X-axis. So when you shift X, you're going left and right. So X is left and right, and Y is up and down. X and Y, that's where that comes from. And then we look at how to measure amplitude. Well, this says each block is worth a half volt. So amplitude is measured from the middle. So if I get this position just nicely here, like that, if I measure from the middle up to the top, I have 2 blocks. Well, each block is worth a half, so that's going to be 1 volt. Notice if I make each block 1 volt, that now I see I only have to go up 1 volt, 1 block, then it's not as tall. But see, if each block is worth less, well, if each block is worth a half, then I have to go up twice as much to get the same value. So here, 2 times a half gives 1, and here 1 times 1 gives 1. Here, 0.1 we're way off the screen, but if we count it up, we would have 10 blocks to get to the top, and 10 times a tenth would be 1. The measurement must be the same in all cases. For the period, you would measure left to right like this, 1, 2, 3, 4, 5 blocks. Each one's worth a second. It's 5 seconds. Notice that sometimes you're asked to go peak to peak voltage. Voltage means Y, and peak to peak means way down here, anti-peak to peak. The very lowest part up to the top. So 1, 2, 3, 4. Each one's worth a half. So that's a half of 4 is 2 volts. Notice that the peak to peak voltage is simply double the regular amplitude. So peak to peak amplitude is simply double the amplitude. How do you obtain frequency of a wave from oscilloscope measurement? Well, you already know how to do that, because that's a fallback to the previous review I gave you, where F is 1 over T, and since T is 5 seconds, this is 1/5 hertz. Or you can use the formula F is 1,000 over T if T is in milliseconds. So if you for some reason measure T is 5 milliseconds, then 5 into 1,000 is 200, it'd be 200 hertz. How's the appearance of the wave change when the time per division change? We already did that. If each block is worth less, then you find that you have to go taller, say, to get your wave, if that's your volt you're playing with. If each block is worth less along the left right, then you have to go a greater distance left right to get the wave. How do seconds, centiseconds, milliseconds kick in? Well, you just have to be careful. This is telling you each block is worth 1,000 milliseconds, so that would be 1 second for each block, and that would be 100 centiseconds for each block. So you just have to keep these straight. Take your time. 1 second is 100 centiseconds, which is 1,000 milliseconds. What role let's see, we did that. Oh, decimals. We're doing decimals next. So let's see what we can do with decimals here. There's one little review here with decimals. So we should memorize these. You really need to know these. Otherwise, you get held back too much in the course. So 1/2 is half a dollar, 50 cents. So this is 0.50, 50 cents. 1/3 of a dollar, 33 cents. So 0.3333 would go on forever like that. You don't need the zero in front here, but I like to put it. It makes it look neat. So 0.33. 1/4 is 25 cents. 0.25. 1/5 of a dollar, 20 cents. 0.20. That one's a hard one. Come back to that one. 1/8 would be split a quarter in half, 12.5 cents. So that's 12 with the 5 there, 12.5 cents. And here, 1/9 is 1/3 of a third. So that's 0. It's all ones. So this 6th one's a little bit tricky, 1/6, and that's a half of a third, and a half of 33 cents. Like a half of 32 cents is 16 cents, so it's close to 16. So it's actually 1/6 with all sixes like this. So 16 cents, 16 and 2/3 cents. So that's a little tricky, perhaps, to remember that one. But most of these are, you can see, are quite friendly, and no one remembers the 1/7, so don't worry about that one. Let's see, time per division and seconds. Know how to work with set the seconds and so you know how to convert from seconds to centiseconds to milliseconds from the first lab, so you should be able to do that. Know the resonance graph, what it looks like, what the axes represent. The resonance graph, that's this thing here. The resonance graph is your amplitude of response of a system when you drive it at different frequencies. So if I drive something at a low frequency, I don't get much result. If I go really high, it gets confused. It doesn't know what to do because you're wiggling your back and forth too quickly. But if you drive it just right where it likes to kind of go at, it goes crazy. So that's the resonance graph. It has a graph that goes up and comes back down again. And the axis here represents the driving frequency. You're driving some system that wants to oscillate. You're imposing yourself, the frequency on there. And this is the response, what kind of response you're getting from the system. Just take your shoe, if you have a shoelace, and play with this. If you shake the shoe back and forth at a low frequency, the shoe won't do much. If you go to high frequency, the shoe will be confused and just not move at all, very high. And if you shake the shoe just right, you'll get a maximum response.